Hello everyone, this is Mr. Zimmerman, and today we're going to talk about lesson 7-3. This is on ways to prove that triangles are similar. In the last section, 7-2, we talked about similar polygons. This time we're specifically going to look at just similar triangles. Looking at the top of the page, we have three postulates that prove that triangles are similar. The first one that we have is side-side-side similarity. Well, that would be if all three pairs of corresponding sides are in the same ratio, or if they're proportional. That would look like this. So to use this side-side-side similarity postulate, again, we're going to want to show this right here. We're going to want to show that all three pairs of corresponding sides are proportional, which means they're in the same ratio or that they make the same fraction. The next one is the side-angle-side similarity postulate. And to use this one, we need one pair of corresponding angles to be congruent, which we can see we have that. And then we need two pairs of corresponding sides to be in the same ratio. So let me write this out for you. So to use this side-angle-side similarity postulate, again, we need two pairs of corresponding sides to be in the same ratio. And then notice that the one pair of angles that is congruent, that's in this case it's angle X is congruent to angle M, that angle must be included in between the two pairs of corresponding sides that are in the same ratio. That's why it's called side-angle-side similarity postulate. And then the last case, we have the angle-angle similarity postulate. And that one just says that you have to have two pairs of corresponding angles that are congruent. So we can see in this third case that we have one pair of angles, angle K is congruent to angle Y, and we also have a second pair of corresponding angles that are congruent. Angle J is congruent to angle X. And that's all we need. And we would know that since the three angles inside the triangle add up to 180 degrees, that these third angles would have to be congruent anyway. Okay? So that's just, all we need is two pairs of congruent angles to prove that those two triangles are similar by angle-angle similarity. Well, let's take a look at example 1. First thing, we have to decide whether the triangles are similar, and if they are, we need to write a similarity statement and explain our reasoning. So in this example, we know that the three angles inside of a triangle have to add up to 180. So if we wanted to find, say for example, angle A in this triangle right here, we could just do 180 minus 38 minus 90. And if we do that, we'll get that this angle A is 52 degrees. Well, now we can see we have two pairs of angles. We have the pair of 90-degree angles are congruent to each other. And we have these pair, we have this pair of 52-degree angles that are congruent. So we have two pairs of corresponding angles that are congruent. We have angle A is congruent to angle D. And then we also have the two, or the pair of 90-degree angles are congruent to each other. So we have angle B is congruent to angle E. So therefore we have angle-angle similarity. So we've shown that the two triangles are similar. And then we also, it says up here at the top that we have to write a similarity statement. So let's do that. So the first triangle, let's call the first triangle ABC, is similar to triangle. And then we have to match up the vertices in the correct order. We can see that we have angle A that corresponds with angle D. Those are both the 52-degree angles. So if I have letter A first in the left side of my similarity statement, angle A is going to correspond with angle D. So that letter has to go first. And then we can see that the 90-degree angles correspond with each other. So angle B is going to correspond with angle E. And then that just leaves us angle F. So there we have our similarity statement. Looking at example 2a, we can see right away that we have a pair of corresponding congruent angles. And then we have, well, these are isosceles triangles where each triangle has a pair of sides that are congruent. And notice that we're talking about the angle that's included between these two pairs of sides that are marked as congruent. And I'm going to put some numbers on here to help you kind of visualize what's going on with this one. So I put some side lengths on my triangles. So in the small triangle, let's say the two congruent sides are both 9 units long, and in the larger triangle, the pair of congruent sides are each 12 units long. Well, then I think you can see that if we set up a ratio of the corresponding sides, we would have, let's see, we have the one pair of congruent included angles, which we need. And then for these two triangles to be similar, we would need these two pairs of corresponding sides to be in the same ratio. So I did put some numbers on here so that maybe you could see this a little bit easier. But what you would have over here then is the length of TU would be 9. That would be divided by its corresponding side length, which would be the length of segment HJ would be 12. And then the same thing, the length of segment TV would be 9, and that would be divided by the length of its corresponding side, HK, which would be 12. And I think you can see that we do have the same ratio, that these two pairs of corresponding sides are proportional. So yes, the triangles are similar. So we would have, this one would be, we should see we have side, angle, side similarity. So we're going to write side, angle, side similarity. And then it also says up at the top that we need to write a similarity statement. We can see that we have angle U corresponding to angle J. So when we go to write our similarity statement here, for the small triangle, I'm going to write triangle UTV is similar to triangle. Well, again, I just said that angle U corresponds with angle J. So the vertex U corresponds with the vertex J. And then we can see that the two angles I marked in red, those correspond with each other. So this is the second triangle is going to be JHK. All right, let's move on to example 2, part B. So in example 2, part B, we're going to have to use the fact that we have these arrows on these segments. And again, that means that those two segments are parallel. And then what we're going to use is we're going to use some pairs of corresponding angles here. So what we could do is we could say that this angle at L and this angle right here at P, those angles are congruent because they're corresponding angles. Again, those are congruent because these two segments are parallel. And then we also have another pair of corresponding angles that are congruent. We would have this angle at M congruent to this angle at Q. And in fact, we'd also have the angle N would be congruent to itself in both of the triangles, the small one and the large one, because angle N is the same angle. But you can already see that I have enough information right here that I've marked that we have two pairs of corresponding angles that are congruent. So this is going to be angle-angle similarity. So we're going to write angle-angle similarity. And then we have to write a similarity statement. So let's make sure we match up the letters in the correct order. This time, let's start out with a large triangle. So we're going to say triangle LMN is similar to triangle. Well, I think you can see by the way I marked the angles, we have angle L corresponds with angle P. And then we have angle M corresponding with angle Q in the small triangle. So we are going to write triangle PQN. All right, let's turn the page and look at example or part C of example 2. Well, at first glance, if you look at part C in example 2, it looks a lot like what we did in part B. So you might be tempted to jump and say, well, hey, this angle corresponds to this angle and they got to be congruent. But you cannot do that because you don't know that segment BC and segment DE, we don't know that those are parallel. So even though they look parallel, don't assume that they are. You have to be told that they're parallel, or they have to be marked with the arrows indicating that they're parallel. So we cannot assume that they're parallel and say that these corresponding angles are congruent. So there's got to be another way to do this one. Well, we do have an included angle on this one. If you look at the picture, the small triangle, triangle ADE, and the large triangle, triangle ABC, they have the same angle right here at A. That's the same angle in both triangles. So we do have an included angle, and then we do have some information given about side lengths here. For the small triangle, that's the 12 and the 15, and for the large triangle, that's the 25 and the 21. So on this one, let's see if those corresponding sides are in the same ratio. If the two pairs of corresponding sides are in the same ratio, because we have that included angle, then we would have side angle side similarity. So that's what we're testing for here. And I think you can see that we have 12 in the small triangle. That would correspond with 21 in the large triangle. So let's set up these ratios of corresponding side lengths. So we have a side length of 12 in the small triangle corresponding with a side length of 21 in the large triangle. And then we have a side length of 15 in the small triangle corresponding with a side length of 25 in the large triangle. And then we want to see if these two fractions are equal. If they are, then we would have side angle side similarity. Well, if we reduce each of these fractions, so the fraction on the right, I'm going to divide the top and the bottom both by 5, and that would give me 3 over 5. And then in the triangle on the left, the fraction on the left, I'm going to divide the numerator and denominator both by 3, and that's going to give me 4 over 7. And I think you can see that these are not equal, okay? 4/7, that does not equal 3/5. So these are not equal. So again, we were saying that this looked like it could possibly be side angle side similarity. Well, because these corresponding sides are not in the same ratio, this is not side angle side similarity. And in fact, these two triangles are not similar. In part D, we have 3 pairs of side lengths. So it looks like in this one, we're going to want to see if we have side similarity. So we need to check and make sure that these ratios of corresponding sides, that they make the same fraction or that they're equal. We're going to do this by saying this side length of 3 corresponds with this side length of 6. So let's see if we get 3 equal fractions when we set up our ratios of corresponding side lengths. I haven't talked about this like I did in the lesson for 7-2, but for 7-3, I'd at least like to point it out, is I'm going to set up my ratios of corresponding sides. And this one I'm going to do the side lengths in the small triangle divided by the side lengths in the big triangle. So let's go ahead and set that up. I have a side length of 3 in the small triangle, corresponding with a side length of 6 in the big triangle. And then I have a side length of 5 in the small triangle, corresponding with a side length of 10 in the big triangle. And then I have a side length of 4 in the little triangle, corresponding with a side length of 8 in the big triangle. And then I just need to make sure that these 3 ratio of corresponding sides, that they're equal, that all these fractions are equal. And I think you can see, if you reduce all 3 of these fractions, they are all going to reduce to 1/2. So they're all equal to 1/2. So yeah, they're equal to each other. And since all 3 pairs of corresponding sides make equal fractions, then on this one we have side, side, side similarity. And then we need to write our similarity statement. With our letters in the correct order, we would have triangle PQR is similar to triangle STU. Moving on to part E, this one looks like it might be, or we're going to test it for side angle side similarity, because we have 2 pairs of corresponding sides, and we have the angle, we have 1 pair of angles that are congruent, and it is the angle included between the given sides. But we can't just say that this is side angle side similarity. We actually need to show that the ratios of the corresponding sides are proportional. So let's do that. And I've made a little note on this one. On this one, I'm going to choose to do the ratios of the side lengths. I'm going to use the side lengths in the big triangle divided by the side lengths in the small triangle. And it doesn't really matter. You could do, you could do little over big, or you could do the way that I chose it, using the big triangle side lengths over the small triangle side lengths. So that part won't matter as long as they come out to be equal fractions. So in this one, let's do big over little. And we see we have a side length of 8 in the big triangle, corresponding with a side length of 6 in the small triangle. So we have 8 again in the big triangle, corresponding with 6 in the small triangle. And then we also have the side length of 20 in the big triangle, corresponding with the side length of 15 in the small triangle. And then we just need to check to make sure that these are equal. So let's reduce these fractions. So in the fraction on the right, let's divide the numerator and denominator by 5, and we will get 4 over 3. And then in the fraction on the left, let's divide the top and the bottom both by 2, and we should see that when we reduce that fraction, let's see, 8 divided by 2, that's 4, and 6 divided by 2, that's 3. So we can see these are equal. Since we have the 2 pairs of corresponding sides that are in the same ratio of 4/3, and we have the included angles, angle K is congruent to angle N, then for this one we do have side angle side similarity. And then we just need to write our similarity statement. So in the large triangle, I'm going to write triangle JKL is similar to triangle, again, putting the letters in the correct order, we would have the vertex at J corresponding with the vertex at M. So putting the vertices in the correct order for the small triangle would be triangle MNP. Moving on to part F, we can see that we already have 1 pair of angles that are congruent, and then we want to note the vertical angles. So we want to say that this angle in the triangle on the left is congruent to this angle in the triangle on the right. And so then, again, that's because those angles are vertical angles. They are congruent. So then we can see right away that we have two pairs of corresponding congruent angles. So these triangles are going to be similar by angle-angle similarity. But let me just write down what we have really quick. So we have angle Y is congruent to angle V. And then we also have the vertical angles. So we would have, in the triangle on the left, we would have angle WXV is congruent to angle ZXY. But again, I think this one's pretty easy to see that we do have angle-angle similarity. And then to wrap it up, we just need to write our similarity statement. Now let's be careful to match up the vertices in the correct order. So for the triangle on the left, let's use triangle WXV and say that that is similar to triangle. Well, before I write this, I guess I should say that we have the unmarked angle here at W corresponding to the unmarked angle at Z in the triangle on the right. So the correct order for this will be angle W corresponds to angle Z. So we have Z, and then the vertical angles correspond with each other. So that would be X. And then we have angle V. We can see that that was marked in the original diagram, and that is congruent to angle Y. I've noticed that I haven't been really circling my answers on these. So again, the two parts, or the two answers that I have for part F, is which triangle similarity postulate we used, which was angle-angle similarity. And then we had to write the similarity statement matching up the vertices in the correct order. So that's our two parts to our answer on part F. Let's take a look at example 3. So in example 3, we have to find the scale factors for parts D and E from example 2. So I set us up in a view where we can look back at our work for those two problems. Also, now remember, our scale factor, all we need to do is make a fraction out of corresponding side lengths. That's it. That's our scale factor. Now, the one thing we want to note on part D is that our ratio needs to be set up triangle PQR to triangle STU. This means that we'll need a side length from triangle PQR on top, and then we'll need a corresponding side length from triangle STU on the bottom of our fraction. And so I made a note here for you that we're going to set this one up as the small triangle over the big triangle. So looking back at our work from part D, you can see that I did already set it up as the small triangle side length divided by the big triangle side length. So any one of these fractions made up of corresponding side lengths is our scale factor. And we're going to want the reduced form of it. So we can see already that we already have this answer. It is right here. It is 1/2. So our answer is 1/2. Then in part E, we need to do the same thing. But we want to take note that we want to set up this ratio of a side length in triangle JLK. That would go on top in our fraction. And then on the bottom, we would need the corresponding side length in triangle MNP. So if you look back up at the picture for part E, you can see then that this ratio would be the side length in the big triangle would be in the numerator, and then the side length from the small triangle, the corresponding side length in the small triangle would be in the denominator. So I made that note for you here. Well, if you look back at part E, you can see that I've already set it up that way. And then any one of these fractions made up of corresponding side lengths would be our scale factor. So we could use 8 over 6. We could use 20 over 15. That's also our scale factor. But then we went ahead and already reduced this to 4 over 3. So that is our scale factor. So our answer for part E is 4 over 3. All right, let's look at our last two examples in example 4. So we want to find the value of x that makes the two triangles similar. Okay, so what we want to do is we want to match up one pair of corresponding side lengths. So we can see that this side length of 18 corresponds to this side length of 27. So let's make a fraction out of that. So I'm going to do this one little triangle over big triangle. So I'm going to do 18 over 27. That has to equal the side length of 22 in the small triangle over its corresponding side length in the big triangle, which would be 8x plus 1. Now we're just going to do our cross products and solve. I can reduce this fraction of 18 over 27. So if I do that, I'll divide the numerator by 9, and that'll give me 2, and I'll divide the denominator by 9, and that'll give me 3. And then I'll have some smaller numbers to work with when I do my cross products. Also, by doing that, now this is my scale factor for my problem right here, 2/3, and that would be set up as the ratio of the small triangle divided by the big triangle. My first cross product, I have 2 times the quantity 8x plus 1. So I have 2 times the quantity 8x plus 1. That would equal my other cross product of 3 times 22. So let's distribute on the left-hand side. So I'll have positive 2 times positive 8x, that's 16x. And then I'll have positive 2 times positive 1, so that's plus 2. And that'll equal 3 times 22, which is 66. Then we'll subtract 2 on both sides, and we'll get 16x equals 64. And then we'll divide both sides by 16. And we'll get x equals 4. Let's use the same process on our last example. And we should see that we have a side length of 30 corresponding with a side length of 24. So in this one, let's go, I'm going to use the ratio of the big triangle over the little triangle. So let's set up our proportion. So we have 30 in the big triangle corresponding with 24 in the small triangle. And we have 3x plus 4 in the large triangle corresponding with 20 in the little triangle. So these should be equal. Let's just go ahead and do our cross products. This time I will not reduce my fraction on the left. So I have my first cross product is 24 times the quantity 3x plus 4. And that will have to equal 30 times 20. Distributing on the left, we have 24 times 3x, that's going to be 72x. And then 24 times 4, that's going to be plus 96. And that's going to equal 30 times 20, which is 600. So then we'll subtract 96 on both sides, giving us 72x equals 504. And then we'll divide both sides by 72, and we have x equals 7. And there you have it. That wraps up section 7-3. As always, thanks for watching, and I'll see you soon in class. Bye.